Thank you for the introduction, and thanks again for changing the seminar time for me. I really appreciate being able to give this talk and not having to get up in the middle of the night. So I appreciate the flexibility. My name is Seth Zippel. I'm an assistant professor at Oregon State University. I'm talking today about measurements that we made from this tower that's shown in the picture on the right-hand side. This was a project that I started when I was at Woods Hole Oceanographic Institution with co-PIs there, Malcolm Scully and Jim Edson. I'm now at Oregon State, as I said, and this project was funded from the U.S. National Science Foundation. So I am going to go through lots of fairly extensive background section because this topic is relevant for sort of two different sets of literature, one about boundary layers and one about how wind waves are made from wind. And I'm going to try and bring them together, but there might be a little more background and literature review than I would normally give in a research talk. So I hope that's all right for everybody. And really, my goal is to relate this small scale fluid flow over surface waves to what you might use in a weather model or a climate model where you have to have some way where the ocean and the atmosphere communicate through a boundary layer scheme and exchange things like momentum, heat, and gases. And so what that looks like, these small scale flows, what I mean is this sort of thing. This is from large eddy simulations from Sullivan et al. In 2018. The black lines show streamlines of wind flow over this surface wave profile. And there's lots of complexity here. There's lots of interesting interactions. And somehow we go from this picture to these bulk exchange rates where somebody takes like a lowest wind speed in their atmospheric weather model grid and converts that somehow to a wind stress. There's bulk algorithms that do this like core. There's other ways that I'll talk about and how that works. And so, like I said, we have to bridge some of two different sets of literature that both of them extend back about 100 years or a little bit more. I'll try and do a really quick overview. I won't be able to get to everything, of course, so don't be offended if I miss a reference that's important or dear to your heart. This is sort of cut a little bit short just because there's such extensive history of literature on both sides. But to start, the simplest form of this problem is a neutral density shear flow over a flat plate. This is a flow that was studied extensively in the early 1900s. And even this type of flow you can see is quite complicated with all of these very difficult to describe swirls and eddies in the boundary layer. And so what we tend to do is try and describe the mean motion and sometimes the statistics of all of the interesting complicated flow features that happen in this type of flow. And researchers in the early 1900s noticed that there's this region called the overlap region or the log region, which will become apparent quite soon. If there's a height away from the plate that is large enough so that you can ignore the effects of viscosity, but far enough away from this outer edge of the flow that's defined by delta, this length scale, then if you're interested in this velocity profile or the shear, the shape of that mean velocity, there's only two ways you can scale the shear. You have U star, a shear stress scale. This is a velocity scale that comes from the total wall stress. And then you have Z, the distance from the boundary. And this kappa parameter is just a scaling parameter for this relation. So it's U star and Z. So it's a pretty simple argument. If you integrate this function to get a function of Z of U of Z, then 1 over Z gives you a log function. And then you have a constant of integration, which is wrapped into this Z naught parameter for now, which I'll get back to later. All right, so this log region arises in what's called the overlap region, where we know we don't have viscosity or delta as a scaling parameter, and it gives us a log function for velocity. This is called a flux profile relation because it relates the boundary layer flux of momentum to the profile of wind speed, velocity in the boundary layer. It depends on one coefficient, kappa, that's used in the scaling analysis, and there's this one parameter, z naught, the roughness length. And if we look at the turbulence budget, which is the statistics that describe all of these small scale swirls and eddies, we get a natural scaling that comes out of that also. The balance is assumed to be from the production of turbulence, which is related to the shear and the stress, the Reynolds stresses internal to the fluid here, and the dissipation rate. And because we have a scaling for shear, we know that the stress also should scale with U star squared. Then we have a natural scaling for the TKE budget, which is U star cubed over kappa Z. Okay, so this was covers a lot of the work done on boundary layers in the early 1900s by folks like von Karman, after which this constant is named. Into the mid-century, people started asking, well, what if it's not a neutral boundary layer? Like, yeah, go ahead.
Can I ask a question? Sorry. Is this how does this compete with the turbulence theory in interior, like Kolmogorov's theory and scaling laws? Does it is it contradicting, or is there any problem with this? Or
It doesn't contradict. It's these flows in this part of the boundary layer should have an inertial cascade with a k to the minus 5/3 slope and a dissipative scale at the smallest scales. The length scale at the largest scales is going to be controlled by the distance from the boundary, kappa z, rather than some Corson scale for a shear flow or an Osmodov scale for a buoyancy limited flow, which might happen in the interior. But in terms of something like, are you asking about like the turbulence cascade or something like that?
yeah, well, you cannot apply these arguments, right? Because there's something, right? There's the boundary.
Exactly right. So if you set the length scale that controls the largest eddies, if those are set by this parameter, kappa z, instead of a more common one like a Corson scale or an Osmodov scale, then everything else still works okay.
Okay,
That
thanks.
makes sense. Okay, but then this was neutral density. So what if we have not neutral density in our profile, some heat exchange at the interface or some stabilizing buoyancy? So this was tackled in the mid 1900s by Monin and Obukhov, and they used more scaling arguments to suggest deviations from that log layer behavior. And I've just sort of sketched it out here. If you have, say, convection, a hot surface, wind blowing over hot concrete, something like that, the extra buoyancy flux from the heat rising off the surface will mix the shear, and you'll have less shear in your velocity profile than you would expect for a neutral log layer. Or conversely, if there's some stabilizing stratification that will inhibit some of the mixing in turbulence in this region, and you'll tend to have more shear than you would otherwise expect for the log layer. So these are encapsulated in functions usually denoted with the symbol phi and a subscript. So phi sub m for shear, phi sub epsilon for dissipation. And these functions must be determined empirically. There's no analytical solution, but they can be bounded by things like the scaled turbulent kinetic energy equation, which is shown here. This is essentially the production term, phi sub m, the dissipation, phi sub epsilon, and then the buoyancy term becomes zeta, the scale parameter, or sometimes called z over L. And zeta, effectively, it's almost like a Richardson number for the boundary layer. So their arguments in this paper were that these functions phi depend only on one parameter, which is zeta. And if you know zeta, you can determine these functions, and that will determine the rest of the problem. So we tend to call this Monin-Obukhov similarity theory, or MOST, or MO theory, after this paper from 1954. And it took a little longer than this early paper, but empirical functions were developed in the so-called Kansas and Minnesota experiments over land in the 60s and 70s, and the 20 years after that first paper was published. Here's what that looks like. This is the picture of the flux tower from that project. And this is a picture of their results for phi m. This is the non-dimensional shear function as uh, as it varies with zeta, that scale parameter. So they have quite nice data, quite clean. I like to joke my partner is from this part of the US, and I like to joke with her that she's from the most horizontally homogeneous land anyone can think of in the United States, because this is a great place to do a boundary layer experiment. Um, and I'm not sure if she thinks it's as funny as I do. Okay, so it took even longer for folks to do this over the ocean. This type of flux tower is a little harder logistically to get and put over the ocean and make sustained observations. You can see here some pictures of some of the platforms folks have used to do this type of boundary layer work over water. This is the air-sea interaction tower, which is in Massachusetts, south of Martha's Vineyard. This is the research platform FLIP, which was operated out of Scripps Institute of Oceanography for a long time. It's a very unique ship that rotates 90 degrees. It floods half of this ballasting compartment that's subsurface right now, and it provides a nice stable platform in the ocean. And this is the RACEX tower, which is a coastal tower where there's been lots of great boundary layer experiments. So these data from these three projects was summarized in a paper from Jim Edson in 2013 that shows the stability functions over the ocean and compares them with the ones over land. Here, this one in the Kansas experiments, this is the Businger-Dyer dash dotted line in this figure. So there's some small differences for the stable regime to the right here, and the unstable regime matches quite closely over the ocean. All right, so application of this theory over the ocean then gives fairly good average turbulent fluxes. We have a log-like profile that's modified by stability. And my talk was on waves. I haven't mentioned waves at all at this point, really. And MOST doesn't really account for waves except their potential impact on the one parameter that I mentioned, the problem Z naught in the log layer. So Z naught can be a function, can be made to be a function of surface waves, but other than that, they don't really have a way to influence MO similarity theory or stability theory. So folks have theorized for a long time that Z naught over the ocean should relate to waves, that sort of intuited that waves impact the roughness of the boundary layer in some way. And indeed, there's some evidence that the drag coefficient, which is related to Z naught or the roughness, can depend on wave parameters like wave age or inverse wave age, or other things. So one thing that's interesting, though, is that Z naught is also really well described by wind speed alone. And there's often a really tight correlation over the ocean between the local wind speed and the wave state that impacts the roughness. And so there's usually some back and forth about, do you use wind speed or do you use waves to influence Z naught here? So in a very bulk mean sense, the wind speed does a pretty good job on average, but there's sometimes wave conditions that are modified from that sort of average wave state you would see for a given wind speed, which can be captured with a wave-dependent Z naught. So to go further into how waves influence this problem, we have to go back again to the early 1900s and start digging into this different set of literature on how the wind makes waves. This is, again, an old problem. Folks have been thinking about this for a long time. I will do my best to get through a lot of this literature, but I might miss some things. So no, it's not because I don't find all of it important, but just that there's, some of it has to be cut for time. So one of the first that's commonly referenced for in the wind over waves literature is Jeffreys' sheltering mechanism. Here's a little snapshot from the abstract here on the formation of water waves by wind. And Jeffreys' idea was that there's a sheltering type mechanism that creates waves. Essentially, it was a flow separation idea that you have flow separation over the wave crests that causes low pressure on the downwind side, high pressure on the upwind side. And just to help visualize this, I went to Wikipedia and found their picture on flow separation. They have these nice streamlines, and you can see they have an airfoil that's creating a disturbance and these eddies developing behind it. All right, so Jeffreys' idea is basically instead of an airfoil, if this was a wavy surface, just like this, that would create high pressure on the upwind side, low pressure in this wake region. And this pressure gradient, this high-low pressure gradient across the wave face creates this net force on the surface, or the stress, okay? It also grows the waves. It results in an energy transfer because the waves have orbital motions. They go up and down, and the upward motion corresponds with this low pressure region. The downward region of the wave orbital motion corresponds with the high pressure region. And when you have pressure velocity correlations like this, it results in an energy exchange through this, what sometimes is called the pressure work. This at the surface is also sometimes called the piston pressure because it's sort of akin to a piston moving up and down. You can think of inflating a bicycle tire with a pump. You push down on the chamber, you create a high pressure region, and you're trying to push down on that high pressure region, and it's hard. It takes work to do that. Or similarly, if it's a two-way pump, drawing up on the chamber can pump air into the tire. It creates an upward motion on a low pressure inside the chamber, and that's also hard to do. It takes work. And so this pressure pattern that corresponds with specifically the vertical part of the wave orbital motion fluxes energy downwards into the waves through this piston pressure or the pressure work at the interface. Really, all you need for this is pressure that's offset from the wave crests and troughs like this. And there's lots of different ways that you can get this mechanism. So Jeffreys suggested flow separation. 30 years went by, and in a review paper by Ursel, I was, for those of you who might be familiar with coastal engineering literature, Ursel has a non-dimensional number that's used more frequently in coastal engineering. I was trained in civil engineering, and so I learned about the Ursel number in school. So it just goes to show that he is a big name in wave circles. He wrote in this review paper, wind blowing over the water generates waves in the water by physical processes which cannot be regarded as known. So basically saying that there were several lab experiments since the work of Jeffreys that couldn't confirm his equations and the pressure difference that he suggested from this sheltering theory. And this inspired several other people to work on this topic in the mid-50s. This is most notably, this is around the time when Monin and Obukhov were developing their similarity theory. The one I'll mention two of them, one by John Miles on the generation of surface waves by shear flows. Here's a picture of the top of their abstract, and you can see here the Orr-Sommerfeld equation is mentioned. And essentially Miles posed this problem as a shear flow instability. So some of you might be familiar with other types of instability analysis. The Rayleigh equation or the Taylor-Goldstein equation is used a lot in stratified turbulence. These are all somewhat similar flavors of a instability problem in fluid mechanics. And Miles effectively posed wind generation of surface waves as one of these instability type problems, found a solution that gave a growth rate that depends on the curvature and shear of the wind profile. All right. So this was in 57. In 2003, this is a snapshot from a Nature paper by Christoph that shows numerical solutions to the Rayleigh equation for wind over waves. These are streamlines. This solid black line is the wave surface profile. And then this dashed red line is what's called the critical layer height. So it's the height at which the wind speed is equal to the phase speed of the waves underneath. You can see from the equation up here that that has particular relevance here. This u minus c equals to 0 gives sort of an interesting part to this equation's solution. And it results in these sort of alternating regions of flow where there's sort of circulation changes direction, right? And it turns out this type of solution also gives offset pressure from the wave crests that can give rise to this pumping mechanism at the interface. The out-of-phase pressure results in an energy flux. But in this case, it's driven by the profile of wind that sets this growth rate, that sets the roughness. And then from Monin Obukhov theory, we saw that the roughness, Z naught, is what's setting the log layer. And then the shape of that log layer is what sets the growth rate. And you can see that these things can be very highly coupled with each other. Okay, so at the same time, there is another theory from Phillips in the same year, 1957, who had a different idea about how waves grow from wind. We tend to call this resonance, but essentially the idea was that there's this broad spectrum of turbulent pressure fluctuations in the atmosphere, and some of those are going to just advect over the water surface with wave numbers that are at the same in the same wave number and frequency or wave number and propagation speed as nascent wave modes in the water. It's going to cause resonance and lead to growth. Turns out that this is leads to a linear growth, whereas Miles' theory leads to an exponential growth. And Miles' theory matches sort of the growth of waves that we see if we measure wave heights as they grow with time or with fetch a little bit better. All right. But this is still thought to control some of the growth at the smallest scales and initial scales from flat water. All right, so bringing some of these together, we have these small existing pressure patterns of turbulence in the atmosphere that resonate with the water surface that create small waves.
Sorry.
Theory.
Yes. Can you make this more precise? Who's winning, Miles or Phillips?
I'll get to that. But Miles, basically. But both of these are incorporated into lots of wave models. I'll show that on the next slide.
Okay.
Waves through this instability mechanism grow, and the shear flow can give more rapid growth rates developed by Miles' theory. And then more recently, there was a lot of work from Peter Janssen at ECMWF, who worked with Miles' theory quite a bit. And then at very high winds, there's still some thought that Jeffrey's theory, this flow separation might still exist, although it's much harder to get observations of this one. So it's possible that all three of these mechanisms exist, and most of the scales we're concerned with, I would say, relate to more Miles' theory. But these things are still parameterized in spectral wave models. So this is a snapshot of the technical manual for SWAN. SWAN is a wave model developed at Delft. but it's pretty similar. This is just one I was familiar with from my coastal engineering background. Um, there are going to be similar source functions in WaveWatch 3 or WAM, other common spectral wave models. They often parameterize both the linear growth from Phillips and the exponential growth from Miles theory, potentially as modified by Janssen's work. And this, if you have a coupled wind wave system, instead of using some bulk parameters for Z naught, you can couple your spectral model to your wind model with, this is a most recently, this was earlier work from Peter Janssen described this relation, but this is a very nice recent paper from Janssen and Bidlow. I think I saw Jean Bidlow on the Zoom call, so hopefully I'm representing his work accurately here. But essentially, this source function for the energy flux to the waves can be related to the wave coherent momentum flux. And this parameter becomes relevant for the roughness length for the atmosphere. And this would be a way to couple your spectral wave model to your atmosphere wind model above. All right, so marine boundary layer flux profiles can be well described by most these log layers with stability modifications. Waves can come into play through the roughness parameter Z naught, which is very much related to the drag coefficient at the surface. And this drag is determined by some of the complex fluid mechanics of wind over waves. I described three primary parts: the linear growth at the earliest stages by Phillips, the shear instability mechanism from Miles, flow instability from Jeffries. And there's more theories that may be relevant that I haven't discussed, like those from Belcher and Hunt in the 1990s. And this is a way to connect these small scale fluid flow over waves to the roughness and then to the fluxes that occur through turbulence. This allows for things like bulk implementation through algorithms like CORE and spectral coupling, like is done through ECMWF wind wave model coupling through that Z naught relation that I showed on the last slide. And I'll note that these are strongly coupled feedbacks, right? From Miles theory, we have the growth rate of the waves is determined by the wind profile, and then the roughness of the waves determines the wind profile. And so you go in a circle like this. So this brings me to some of my research questions. How is energy conserved between wave growth and MOST in the boundary layer? So the energy budget considered in MOST doesn't have any sinks for the surface waves, but we know that waves carry lots of energy with them. And that energy tends to come from the wind. And so there's sort of this disconnect in terms of the energetics between wind wave growth and the similarity theory I described. That would be carried out through this piston pressure or the pressure work mechanism that I mentioned, the alternating high pressure, downward velocity, low pressure, upward velocity that sets up on the interface. But it's quite hard to measure this in the field co-located. These are fairly small pressure fluctuations. And then even from our original scaling arguments that gave us the log layer, we were able to make these scaling arguments because there were no other relevant scales for motion. But when you add surface waves, you have all sorts of additional scale parameters. You have the phase speed of the waves, you have a wavelength, you have a wave frequency, and you have, it makes it a little harder to make some of these same scaling arguments that you can ignore all of those scales, right? So this has led some people to call into question whether we have MOST like boundary layer profiles over the ocean, despite some of the evidence taken from Edson and those different platforms that the shear matches like it does over Kansas. So This leads to our project. We put a tower in Buzzards Bay, Massachusetts. This is near Woods Hole, where I was a scientist at the time. Some of you might recognize this sort of distinctive shape of Massachusetts. Boston is up this way. New York is down that way, down the coast. This embayment is 13 meters deep where we place the tower, and it's fetch limited. So the waves are pretty short, there's no swell, and the tides are relatively small, which makes it a nice place to try and get measurements very, very close to the surface of waves that you know sort of how high they're going to get and how much the water is going to go up and down from the tides. Because of the fetch limitations and this depth, the waves are still in deep water when compared with this non-dimensional wave depth, the depth over the wavelength. And so that's still a good representation of deep water waves, which is important because waves change their shape as they move into shallow water. So you'll notice we had these three primary booms. Each of these booms had a sonic anemometer to measure fast response 3D velocity and a pressure sensor that was very sensitive and had this sort of unique flow intake head to minimize the effects of what's called wind noise in a lot of the pressure literature. Basically, if you put a sensor in a flow, it creates its own pressure pattern by its own presence, and that can be very hard to decouple from the signal that would be in the flow without the sensor there. And so we make these special heads or intakes to minimize that effect and to try and measure the ambient pressure. And then you'll also notice we had a laser wave gauge to measure that was really well aligned with our pressure velocity measurements, so we could measure the sea surface the same place and at the same time right under this array. And what that looks like is this is a 25-second snapshot from the tower. The top panel shows normalized pressure perturbations. The bottom panel shows the wave profile measured from the LiDAR, from the laser wave gauge. It's a time series, so the wind and the waves are going right to left, right? You see the downwind part of the wave first, and then the crest, and then the backside of the wave. And you can see that this pressure signal from all three booms is going up and down coherently with the waves at the surface. The first thing you notice is they're mostly out of phase. You have low pressure during the crests, higher pressures during the troughs. But if you look closely, especially around this 10-second mark, you can see they're a little bit offset. So the crest is just to the right of this 10-second mark, and the lowest pressure region is a little bit to the left or just on the 10-second mark. And so that small phase shift from 180 degrees means we have a little bit of pressure, low pressure in the downwind, the downward stroke of the wave orbital motion, and a little bit of higher pressure during the upward stroke wave orbital motion. And that's going to create this pressure pumping mechanism that I described before. Okay, so this is the fact that there's this, even if it's a small phase shift, that any phase shift is going to create an energy flux down through the surface. All right, so here is an overview of the winds and waves from the two different deployments of the towers. Each one lasted about 2 months. The top panel shows wind speeds from 4 different booms, actually. The middle panel shows the significant wave heights, which were, a meter during the high wind events when we had winds up to, 15 meters per second or so, but were generally quite small. This bottom panel shows the magnitude squared coherence between the atmospheric pressure and the sea surface elevation eta. So this is how much the pressure is varying in the atmosphere with the waves underneath. Yellows show really high coherence. You'll notice a couple things. Actually, the highest coherence is when the waves were big and then die really suddenly. That's not something I'll be talking about too much today. But you see that signal come up a couple times here, especially in the fall. We had more variable winds. That's actually because we still have some waves, and then the noise or the turbulence that's also existing in the background becomes very small, which gives you very high coherence. I'm going to focus on these patches like this one during the storms where we had high winds, big waves, and sort of middle levels of coherence around 0.6 or so, like this and like this. Um, and that's when we tended to have strong wind wave growth. And as I mentioned before, that pressure work, the PW correlation, that is what impacts the turbulence budget in the atmosphere. Okay. This is a pretty complicated plot, so I'll try and walk through it really slowly. What I'm plotting on this axis, this is a frequency spectrum of the co-spectrum of pressure work, the real part of the co-spectrum of pressure work. It's normalized by the magnitude of this flux, so that we can show several different wind speeds together. And so this is just to show the shape of the spectrum of this flux, okay? Positive values denote an upwards flux. That's actually waves driving the wind that's sending their energy upwards. And then the pumping mechanism I described in this schematic is negative values, downward fluxes from the wind to the waves. I'm going to show lots of different lines that are colored by the wind speed at 10 meters. Small wind speeds are in blues, moderate wind speeds are greens, and then high wind speeds are in reds. And then this critical layer height that I mentioned, the red value where the wind speed at the height of the measurement is going to be equal to some phase speed that exists in this spectrum. And so that's going to be denoted with vertical lines that are colored by the averaged wind speed that we've correlated together. So if you were to the right, the waves are moving slower. That means the wind is going to be faster than the waves at those frequencies. And as you move to the left of these vertical lines, the waves are going to be faster than the wind because longer waves travel faster, okay? So as you step through at the low wind speeds, we have pretty much most of the fluxes are to the left of this vertical line, and they're upwards. As we increase the wind speed, you'll see that we see both positive and negative fluxes, and it's not perfect, but roughly corresponds with this critical layer frequency or this height where the wind speed and the phase speed are equivalent, all right? And then at the highest wind speeds, this critical frequency goes far to the left of where all the energy in the spectrum is, and we have only now downwards negative fluxes. If you're familiar with looking at wave spectrum, you might squint at this and say, hey, that kind of looks like a wave spectrum, and you'd be right on. This is very coherent with the surface wave spectrum. All right, so this is sort of what it looks like when we go and we make these measurements of pressure work. And so we can go and look for signals of this in the turbulence energy budget, the TKE budget. This is what was suggested from that log region in most. This is dimensional, not non-dimensional at this point. We have the dissipation rate here on the vertical axis. We have the production and the buoyancy flux, the sources on the horizontal axis. We can estimate these because these involve gradients. Can estimate them between the boom levels using the shear estimated from the difference between wind measured at two heights. And it's actually, we get really good agreement for the turbulence budget. Very close to 1-to-1 over several orders of magnitude with lots of data from two different levels. Except, right, so this is just like that budget for a reminder. This is that turbulence budget that I showed on, I think, slide 2. Except at these very highest winds, when we have the biggest storms, the most energy, we start to dip just to the right of this 1-to-1 line here. And so that's a little indication that we're leaking some energy out of our turbulence budget, and it needs to be accounted from something. So a good candidate is this pressure work term into the waves that we measured. The next question, though, is does this impact our stability functions for similarity theory? So we can take our measured shear, normalize it by u star over kappa z, to estimate phi m, that stability function, plotted as z over L. And in fact, we get really good agreement with both the previous data from Edson over the ocean and the current phi sub m functions that are used in parameterizations like core. For reference, the green line shows the Businger-Dyer curves. That's what was developed over land. And similar to Edson's data, we see a small change in the stable regime, but generally pretty good agreement. My data here is the blue diamonds. Jim Edson's data is the gray circles. And I already mentioned the curve colors. If we look at the similar function for the dissipation rate, here these colored curves, this is what would close a turbulence budget that's been non-dimensionalized and has this shear function form. Okay. This doesn't look quite as good as the shear function. You can see some deviations, particularly in this slightly unstable regime close to zero. We see much less dissipation than you might expect from these curves, and a little bit more during the slightly stable regime. Okay, so what's going on? If we separate out some of the data during when we had these strong storms and we measured lots of pressure work, and we average those, we see that's even farther from this line. Okay, so if we increase the wavy pressure work, we show even more, even smaller dissipation compared to these baselines, which is again suggesting that the waves are responsible for drawing down energy, and it's resulting in less turbulent dissipation than you would otherwise expect for a boundary layer. When we plot shear, we do the same thing. We plot data where there's strong wind wave growth, and as you know, the error bars are a little bigger, and there's not as much of a deviation from these shear curves. This is really zoomed in compared to the plot I showed on the previous slide. So, you know, maybe if you squint, this last data point or two might be a little bit smaller, but for the most part, these are not significantly different from the baseline. Okay, so it's the waves are drawing down dissipation, but they're not modifying the shear by that much at these speeds and wave states. But the thing that really puts it together is doing a full energy budget. So if we look at those high winds speed events like this storm in May, we can compare the estimate of the energy budget from most, which is the production plus the buoyancy minus the dissipation rate. It's positive, which means that there's less dissipation than there would be for a boundary layer to close this budget. And that energy needs to be taken down by some other process. That's shown by the blue dots, which is moved into the blue curve with a 6-hour moving mean filter. In orange squares, we're showing the directly measured pressure work. This is the energy flux into the waves as we've estimated it from those booms. And that seems to match decently well to the blue curve once you do a little smoothing. And then in purple, this is what you would estimate as the input to the surface waves from a spectral wave model. So if you take some of those, this is, I believe, the Janssen's wind wave input function that's parameterized in WAM, and there's options flags for it in other wave models. That is shown in purple with some 50% error bars for one of the coefficients. And that also matches quite nicely. So it's all energetically consistent, at least for this event, when we look at connecting the turbulence budget to the energy flux that goes into the surface waves. You know, of course, as an observationalist, if you do something once, maybe you should stop before you get results that aren't quite as good. So if you look at the fall data, it doesn't quite match up quite the same way, quite as nicely. I have a colleague who's been looking at this more, trying to tie up a few things. We suspect that one of the pressure levels has a little bit of issues. It could have been one of those static probe heads was damaged. He's been redoing this budget in a slightly different way and just using 2 of the 3 booms, and it's lining up quite nicely in his work. And so I didn't want to share his work without his permission for this talk, but he's working on a draft for a publication that will show that this is coming together a bit more. All right, so it is 7:45. I'll get to my summary, so there's some time for questions, but most of the time this balance that you'd expect in a normal law of the wall or Monin Obukhov profile seems to match over the ocean, right? Most of the time these terms are balanced. It's only during the high winds when we're really just off the surface that we start to see some of these deviations. Those deviations, result in these strong downward negative pressure work fluxes through this pumping mechanism. And when we include that in our energy estimates, it seems to close the rest of this energetics balance. So it accounts for some of this missing energy that would otherwise be taken up by the dissipation rate in a normal wall profile. Despite the fact that we see this in dissipation, the shear function, which we use really heavily for estimating fluxes in our boundary layers, doesn't seem to be that affected, at least at the wind speeds that we measured and the wave states that we measured. So this was fetch limited waves, 12 to 15 meters per second. It seems relatively unaffected. So there's been some criticism of MOST and core over the ocean, stating that sometimes if your measurements are inside the wave boundary layer, you might not get the same shear profile. But at least from this data set, it seems like it's actually quite robust, even when we know we're in that wave boundary layer and we see and measure energy fluxes that are needed to close the energy balance. It still is, it draws first out of dissipation, and the shear is not affected until possibly much higher wind speeds. So I can just share some quick snapshots of some ongoing and future work before I take questions. There's a postdoc who is working with me, who is at Woods Hole, Yun Chang, who has a JPO paper that's under revisions right now. He's gone through and compared numerical solutions to the Rayleigh equation to some additional observations. We basically took the Buzzards Bay mast and put it on the ACIT tower, which you saw that Edson had used for his paper in 2013. Is comparing to at higher winds if we still see this type of agreement, and is seeing fairly good agreement between the observations and the Rayleigh mode solutions. But at the same time, there's some evidence for nonlinear mechanisms as well. So this is that time series from Buzzards Bay that I showed. You can take these essentially a transfer function from the linear wave coherent part, and that explains most of these pressure fluctuations that we see in the Buzzards Bay data. If you look at this new data set from ACIT, we can do the same decomposition, and you'll see we have occasionally these big jumps of low pressure. They're not occurring for every wave. They're sort of intermittent, but they are 90 degrees out of phase with the wave crest. And we think these are maybe some evidence for Jeffreys shear for flow separation events. You notice the wave heights here, these are -2 to +4 meters compared to the -1 to +1 meters on this scale. So these are much bigger waves, likely breaking with lots more complexity here. So I think there's still more interesting work to be done, particularly at the high winds. But I will leave it here at the summary and take questions. So thanks, everybody.